A loan officer at a regional bank denies a small business credit application. The applicant invokes their rights under the Equal Credit Opportunity Act and requests an explanation for the denial. The bank's machine learning system automatically generates an explanation, listing the top three factors that influence the decision: debt to income ratio, time in business, and industry classification. The explanation is technically accurate. It was produced by a SHAP model running alongside the primary credit model, estimating which input features most influence the output score. However, the explanation cannot specify which exact data values triggered those factors, which version of the credit model was active at the time of the decision, or whether the industry classification used matched the applicant's business license. The applicant's attorney doesn't care about feature importance scores. The attorney wants to know precisely what the system knew, what it decided, and why. The explanation the bank can provide and the explanation the attorney needs are not the same, and the gap poses regulatory risks. This is Explainability in Product Machine Learning, ML, Part 32. Why the difference between an explanation and an approximation determines whether your machine learning system survives its first serious audit. Section 1. What explainability actually requires. Explainability in production machine learning means different things depending on who is asking and what they need to do with the answer. A data scientist asking why a model produced an unexpected output needs feature attribution. Which input variables drove the prediction, and in which direction. Shapley Additive Explanations, or SHAP, addresses this by computing the contribution of each feature to the difference between a specific prediction and the average prediction across the dataset. Local Interpretable Model Agnostic Explanations, or LIME, addresses it differently by training a simpler interpretable model locally around a specific prediction to approximate how the complex model behaves in that neighborhood. Both tools are genuinely useful for model debugging and development. Both are approximations. Neither reconstructs the actual computation that produced the prediction. A business stakeholder asking why the system recommended a specific action needs a plain language explanation that connects the recommendation to a business logic they can evaluate. Gradient-based attribution methods like integrated gradients, available through the Captain library for PyTorch models, provide more technically precise attribution for deep learning models than SHAP or LIME, but require more expertise to interpret and communicate. A regulator, auditor, or legal reviewer asking why the system made a consequential decision needs something none of these tools natively provide. They need a reconstruction of the full decision chain: what data the model received, what version of the model processed it, what the model produced, and how that output connected to the action taken. That is not a feature importance score. That is a provenance chain. Section 2. The tool landscape. On the open source side, SHAP is the dominant explainability library across the machine learning ecosystem. It works with three base models, neural networks, and linear models with different computational approaches for each. CAP is the PyTorch native attribution library maintained by Meta, offering gradient-based methods that provide more precise attribution for deep learning models. LIME remains widely used for model-agnostic local explanations despite being computationally expensive at scale. On the commercial side, Fiddler provides explainability integrated with model monitoring, connecting feature attribution to drift detection so that changing feature importance over time surfaces as an early warning signal for model degradation. Arthur offers similar integration monitoring explainability with strong tooling for native language model explanations. DataRobot builds explainability direct into its automated machine learning unit platform, making it accessible without requiring separate implementation effort. The commercial tools each earn their costs in regulated industries where explainability must be continuous, auditable, and integrated with governance workflows rather than run on demand during model development. The open source tools earn their place in development environments where practitioners need fast iteration and deep technical access to attribution methods. Section 3, where approximation becomes a problem. Post hoc explainability tools approximate model behavior by observing inputs and outputs rather than instrumenting the model's internal computation. This distinction matters in three production scenarios. When the explanation contradicts the model, post hoc approximation can produce feature attributions that are locally accurate but globally misleading. A SHAP explanation that identifies feature A as the primary driver of a specific prediction may be correct for that prediction, while obscuring that feature B drives the model's behavior across the broader population of similar cases. The explanation is technically defensible and operationally misleading. When the model changes, but the explanation methodology does not, attribution scores from one model version can't be compared directly to attribution scores from a subsequent version. Organizations that use explainability for regulatory compliance need versioned explainability that tracks alongside model versioning in the model registry. When the explanation must connect to external knowledge rather than internal model behavior, post-hoc attribution methods have no mechanism for that connection. A feature importance score for industry classification has no formal relationship to the industry classification ontology in the bank's knowledge graph. The explanation floats free in the formal definitions that compliance frameworks require. Section 4, where the semantic layer changes the calculation. The provenance and grounding infrastructure from parts 22 and 23 is what moves explainability from approximation towards reconstruction. When machine learning model outputs are grounded in formally defined knowledge graph assertions, explainability stops being an estimate of which features mattered and becomes a trace of which verified facts the system reasoned over. The credit denial explanation does not cite a feature importance score for industry classification. It cites the specific industry classification triple, its source, its timestamp, and the formal definition in the ontology that the compliance framework references. The explanation is not an approximation of the model's behavior. It is a reconstruction of the knowledge the model operated on. This is what the semantic layer gives explainability that post-hoc attribution method can provide independently. A formal vocabulary for describing not just which inputs influenced the output, but what those inputs formally meant, where they came from, and whether they were valid at the moment the decision was made. Section 5. Why this matters. Production explainability that satisfies the development team and production explainability that survives a regulatory examination are not the same capability. The tools that survive the first purpose, SHAP, LIME, CAPTUM, and their commercial equivalents are necessary and insufficient for the second. The infrastructure that makes the second possible is a provenance-aware, semantically grounded architecture this series has been building toward. The loan officer's denial explanation and the attorney's audit request will eventually converge on the same question, not what factors matter statistically, what did the system actually know, and can you prove it?